This is part 3 of Unit 4, Lesson 3's videos on relates and context of other topics other than motion. So we have a series of examples to do in this last video to finish up our notes. So example 6 begins by showing us a table that represents the cost and revenue for the production of a widget. And we're to use the table to answer the following questions. So first, what is the price of a widget? Well, we can figure that out by taking the revenue and an X value. So we can see in our table here, when we produce 200 widgets, our revenue was $600. So we can take 600 and divide it by the 200, and we can see that each widget is $3 per widget. That's our cost per widget. Part B then asks, what are the fixed costs? Well, fixed costs happen when X equals 0. And again, those are things like rent and insurance and taxes and things of that nature. So when X is 0, we have a cost of $800. So our fixed costs are $800. Next, at what production level X is the profit of the widget maximized? Explain your reasoning. So what we're going to see is we're looking for where our profit function, which is pi of X, is greatest. So where do we find that? We find it where there's the biggest difference between, because remember, pi of X is found by taking our revenue and subtracting off our costs. So looking at these two entries here, we want to find where we have the greatest difference in prices. And you can see that at 1,000 items, we have the largest difference because we have a revenue of 3,000 and our costs are 1,800. Other than that, I mean, our costs aren't that different through the rest of the values for X, but our revenue definitely changes. It does take a big jump there. So at 1,000 widgets, and you can check all of them, pi of X is going to equal R of X minus C of X. So in this case, we're going to have 3,000 minus 1,850 gives us our maximized profit of $1,150. Okay, so that problem is pretty straightforward. Nothing tricky there or anything. Next, example 7. When a backpack production is 5,000, marginal revenue is $5 per backpack, and marginal cost is $4.65 per backpack. Would a maximum profit be expected to occur when the production levels are above or below 5,000 packs? Explain. Well, what you want to remember is that marginal revenue happens at the slope of the tangent line of our revenue function at specific values. And same with our marginal cost. Marginal cost is going to be the slope of the tangent line of our cost function. So then we want to see that if we're looking at 5,000 units, so add 5,000 units, our marginal revenue is greater than our marginal cost. So if we want to exploit that, the company will make extra revenue that's supposed to be an R. I should say more extra revenue. Let me put a more in there. Then it'll spend Because remember, your marginal revenue is the addition revenue that you're going to have. And right now that's at $5 when you're at 5,000 backpacks. And your marginal cost is at $465. So we have more additional revenue than we will spend for additional costs. So the max profit, sorry, I'm running off the paper, should occur above 5,000 units. Could be right at 5,000 units, but we would need more data to be able to answer that in more detail. It's just the idea of understanding that marginal revenue is the addition of extra revenue you get for producing more. So there's enough of a gap between the marginal costs and the marginal revenue to make it worth it to go above 5,000 units. Okay, so now let's finish out with some other types of related rates that aren't related to money either, but do happen. So example 8, Gabby is working on a project that watches the decline in great white sharks in the Atlantic Ocean. The function S of t equals 3,570 e to the negative 0.2 t gives the number of sharks t years since she began working on the project. Find the rate of change for the number of sharks in the ocean after 3 years. So if we want the rate of change, we definitely want the derivative. So we're going to find S prime of t. So we're going to keep our constant. We're going to take the derivative of e, which is e. And then this is going to be a chain rule because that is itself its own function. So we're going to take the derivative of negative 0.2, and we get negative 0.2. And multiplying these two together, we're taking 2/10 of 3,500 or 3,570. We get negative 714 e to the negative 0.2 t. Okay, so we want S prime of 3, so we're going to substitute 3 in there. And again, like a lot of these related rate problems, you really are expected to have a calculator for them. So this is approximately equal to negative 391.852. So we can say the number of great white sharks is decreasing at a rate of 392 after 3 years. Okay? So we're losing 392 or more after 3 years. Next example. Omar uploads a funny video of sugar gliders on his Instagram account. Someone has to tell me what a sugar glider is. I don't know what that is. The video went viral rapidly. The number of views t days after Omar uploaded the video can be modeled by the function v of t equals 243 e to the 1/2 t. What is the instantaneous rate of change in the number of views 5 days after he uploaded the video? So again, we're going to take the derivative of v of t. And when we do that, we're going to keep our constant. We're going to keep our e function. And then we have to take the derivative of that, the chain rule. So that is going to be 0.5. So v prime of t is going to equal half of that, which is 121.5 e to the 0.5 t. So we want to know how many views he has after 5 days. So we want v prime of 5. So it's going to be 121.5 times e to the 0.5 times 5. So v prime of 5 is approximately equal to 1,480.173. That's a lot of views after 5 days. I hope sugar gliders are funny. I don't even know what they are. The number of views of Omar's video and since it's positive, we can say is increasing at a rate of 1,480 views per day. That's a lot of views. An increase in views. It's not the actual number of views, it's the increase in number of views. Okay, and finally, our last example. Using the following table of values for the numbers V of T, which is gallons of water in thousands per hour that are flowing into a retention pond T hours after a severe thunderstorm. Okay, so it's rained outside, water's everywhere, and now we have a retention pond that's filling up. So what is the interpretation of V prime of T? So V prime of T represents the instantaneous rate of change I feel like I missed something in that word. Yeah, I did. I missed half the word. Why is this not working? Okay, there we go. Instantaneous. And that doesn't look right either. Instantaneous rate of change. We'll keep going, barring my spelling inadequacies, of the water flowing into the retention pond. I know what that is. T hours after the storm in thousands of gallons of water. I try to stay away from cursive writing, and then I start doing it. Okay, part B says estimate V prime of 2, explain the meaning in context. So we're estimating it, so we're going to use a difference quotient to find the slope. So we are going to look in two places. I mean, we should do this twice. They should be about the same. You're going to see these numbers are a little off. So we're going to do a difference quotient between 1.5 and 2, and then we'll do another one between 2 and 2.5. So starting with that one, the red one, since I have that circled last, I'm going to do 1.24 minus 1.15, and I'm going to subtract 2.5 minus 2. And when I do that, I want that to be approximately equal to the blue rectangle I created here, which would be 1.15 minus 0.93 over 2 minus 1.5. Now these should be relatively the same. And what we get for the maroon one is we get a V prime of 1.8, and the other one we get a V prime of 0.44. So what we can say then is that V prime of 2 is between 0.18 and 0.44, and it tells us that after 2 hours, So either 180 to 440,000 gallons of water are flowing into the pond. Okay, and then the last part, part C, says, when does a rainwater flow begin to slow down? Estimate the instantaneous rate of change at this time. Okay, so what we're going to see if we look at our table again is, let me erase the stuff I have on there. We see that the flow rate is going up here, and then right here is where it starts to slow down, between 2.5 and 3 hours. Okay, so we know that the flow rate is going to change between, we can say sometime between 2.5 to 3 hours. And we're going to estimate it. So using those numbers on our table for V prime of 3, we're going to do a difference quotient, and we're going to have V prime of 3 is approximately equal to 1.05 minus 1.24. That's all over 3 minus 2.5, taking those numbers out of the table and substituting them in our difference quotient. So this is going to be equal to negative 0.19 over 0.5. And so this equals negative 3.8. So what does this mean? This means that we are losing negative 380,000 gallons of per hour. It's not of, it's just per hour. Okay, so what we're going to do in the next lesson is we're going to build on this and talk more about how we use related rates when we have different things going on. In other words, let's say we know a volume, but we want to talk about the surface area. How is that going to change based on certain restrictions on the volume, or vice versa? What if we know the dimensions of a package, but what if we put them together in a different way? So how is that going to affect the surface area and the volume of the package? But for now, this is a nice beginning for our related rates.